So, spanning off those websites that give you a lot of information, I'd like to touch base again on another important law that was passed known as the Toxic Substance Control Act of 1976. This law screens and regulates chemicals to minimize human health risk. The United States produces about 125 million metric tons or 280 billion pounds of synthetic chemicals and creates 200 million metric tons of hazardous waste each year. As I've expressed already, there's different laws that have been passed to regulate the chemical production and hazardous waste disposal, and many of these laws deal with end-of-pipe controls in terms of controlling what's going into the air or onto the land or into the water. But the TSCA law was specifically set up to require pre-manufacturing notification of any new chemicals. So basically, a company must inform the EPA 90 days before they import or manufacture a chemical substance that's not currently in commercial use. The EPA then has 90 days to approve the chemical or place restrictions on its use to reduce exposure to people and the environment. If the chemical could be hazardous based on toxicity data, then what happens is the EPA requires the manufacturer to conduct additional toxicity testing. So this law basically states that EPA must examine chemicals that were in commercial use or being proposed for commercial use. Currently there's over 83,000 different chemicals in the TSCA inventory. By the way, this law was amended in 2016 by the Chemical Safety for the 21st Century Act. For the first time, it requires EPA to evaluate the safety of existing chemicals that were in commerce, starting with the most likely to cause risk. It also requires EPA to evaluate new and existing chemicals against a new risk-based safety standard that includes explicit considerations for vulnerable populations. It empowers the EPA to require the development of chemical information necessary to support these evaluations and establishes clear deadlines for both the manufacturer as well as the EPA in order to timely review the information and identify risks with the chemicals. It also increases public transparency of chemical information and allows the information to be available to the public. In addition, I'd like to point out that TSCA excludes foods and food additives, drugs, and cosmetics. These items are regulated under the Federal Food, Drug, and Cosmetic Act. In addition, it excludes pesticides because they're regulated under the Federal Insecticide Fungicide Act, FIFRA, which I've already mentioned in an earlier slide. So, what types of chemical hazards do we face? Many chemicals in the environment can be hazardous to humans and can cause cancer or birth defects or disrupt the immune system, the nervous system, or the endocrine system. The link between hazardous substances and health problems is hard to establish, and it's sometimes very difficult to create a statistical correlation between an exposure to a chemical and the adverse health effects. So it does make it challenging. I do want to make sure you understand the term toxicology. That's the term for the science that studies the impact of toxic substances on human health. So let's make sure you are clear on what a hazardous material is. A hazardous material is any chemical that presents any of the following hazards or risks. And it only has to be one of these. Ignitable, a substance that catches fire easily, like gasoline. Corrosive, a substance that corrodes tanks and equipment, like acids. Reactive, meaning the chemical is unstable in the presence of oxygen or water and may explode or create toxic fumes if mixed with water. And then toxicity is when the substance is detrimental to human health if it gets on their skin or is breathed in through their nose or eaten on some form of food. So, please understand that the term hazardous is not synonymous with toxic. Toxic is only a part of the numerous hazards that we face when we work with chemicals. Hence, they could be reactive, corrosive, or ignitable. This is an example of the different placards that are used on trucks that haul various chemicals over our roadways. So, in terms of toxicology, we first determine if a chemical is harmful based on its route of entry. How was the person exposed to the chemical? Did they breathe it in through inhalation, which is considered to be the fastest exposure route because the chemical gets into our bloodstream directly through our lungs? Did they ingest it orally by eating something or something being placed in their mouth? Or did they get it on their skin through a direct contact, which is considered to be the slowest exposure route? The term dose is on the screen in front of you, and it's the amount of chemical that was ingested, inhaled, or absorbed through the skin, which reacts with the body to cause harm. And it does take into account the weight of an individual. The term exposure refers to the amount that the body comes in contact with the air that we breathe, the food that we eat. It's a little bit different than dose because it does not take into account the weight of the individual. The other thing that determines if a chemical is harmful or not is the length of the exposure and the frequency of the exposure, as well as the age of the person, whether they're male or female, and the genetic makeup of the individual. In 2005, an environmental working group analyzed umbilical cords from the blood of 10 randomly selected newborns in U.S. hospitals. And they found that there were over 287 chemicals detected in the umbilical cord blood. 180 of those chemicals could cause cancer in humans or animals. And about 217 of those chemicals could cause brain and nervous system problems in test animals. And about 208 of those chemicals detected could cause birth defects or abnormal development in test animals. So the point that I'm trying to make here is that young children are more susceptible than teens or people in the middle age bracket, and that's because of their age and the fact that they put a lot of stuff in their mouth, as well as have a smaller per unit of body weight than adults. And in addition to that, children can have less developed immune systems and body detoxification processes than adults. So children are considered to be more susceptible to exposures than any other age bracket. So, two terms to be familiar with: acute toxicity and chronic toxicity. Acute toxicity refers to a short-term exposure, and its effects can range from dizziness to maybe a rash or to death, depending upon the actual dose. They are typically immediate health effects which appear shortly after the exposure and usually the result of a high concentration short-term exposure. So we can typically connect, you were exposed to something and here's the health effects that you have. Like I mentioned, the health effects are immediate or rapid, and these health effects are typically reversible unless death occurs. The health effects can be minor or severe depending upon the dose of exposure, and the chemical cause and effect is typically known, but not always. Chronic toxicity involves a long-term exposure over a long length of time. Usually it involves a low dose of exposure, which results in small doses over a long time frame. The health effect from this kind of exposure scenario can occur months or even years after the exposure. Oftentimes the health effects are not reversible, and it's typical that the chemical cause and effect is unknown due to the long delay of health effects from the exposure. Two factors that influence toxicity are bioaccumulation and biomagnification. And the graphic on the screen tries to depict bioaccumulation in fish over time, where in the same 3 fish, the concentration of that contaminant or chemical accumulates within those same 3 fish. And then biomagnification is depicting how the chemical magnifies in concentration as it moves up the food chain. DDT is a chemical that's been banned here in the United States mainly because of its ability to biomagnify up the food chain and persist in the environment. So the pesticide DDT can be present in water and it's taken up by zooplankton. Small fish can ingest that fat-soluble DDT, which becomes concentrated in their body fat. The DDT also accumulates in fish-eating birds. As illustrated, tissue concentrations increase at each level of the food chain, and for humans, the magnification that occurs in our food chain may be as much as 75,000 to 150,000 times greater than the original concentration in water. Please remember that the lethal dose for DDT is 100 milligrams per kilogram or parts per million. So magnifying this up the food chain can definitely pose a threat to human health. Another example that I'd like to give you is from the Arctic Monitoring and Assessment Program. What was done is that caribou were sampled in Canada's Northwest Territories, and it was discovered that caribou had as much as 10 times the level of PCBs as the actual lichen on which they grazed, which is a small plant. PCB levels in the wolves in that area that fed on the caribou were magnified nearly 60 times as much as the lichen that were fed on by the caribou. Again, just another example of biomagnification. This is a graphic depicting what happens with biomagnification of DDT up the food chain. And I'd like to provide you with some specific examples of what DDT has done as it has biomagnified up the food chain. In terms of birds, what happens is that the DDT doesn't kill the bird outright. Rather, the DDT impacts the bird's calcium metabolism and results in the bird laying eggs that have very thin eggshells. The brown pelican and the bald eagle tend to find omelets in their nest since their eggshells are unable to support the weight of the birds. So shell thinning resulted in the decimation of the brown pelican population in much of North America and almost exterminated the peregrine falcon in the eastern United States and southeastern Canada. Shell thinning also caused lesser declines in population to the golden eagle and the bald eagle and the white pelican, among other bird species. Once this link was discovered between DDT and declining bird populations, DDT was banned in the United States in 1972. The reduced bird population started to recover quickly thereafter, and species as different as ospreys and robins returned to the pre-DDT levels because of success in reproduction. Furthermore, the peregrine falcon has reestablished itself in the eastern United States as a result of biologists using captive reared birds and breeding them and releasing them. The brown pelican populations have also recovered to the extent that the species no longer warrants an endangered status except for in California. So the banning of DDT has helped these birds recover in their populations, but it has also created other pesticide problems. For example, the newer organophosphate pesticides that are being used instead of DDT have replaced organochlorines, such as parathion, and they are less persistent, so they do not accumulate in the food chain, but they are nonetheless still highly considered toxic. Parathion is applied to winter wheat, for instance, and killed some 1,600 water birds, mostly Canada geese, in Texas Panhandle just in 1981. This slide just shows you how to understand chemical concentrations in terms of parts per million or parts per billion. A part per million is similar to $1 in $1 million. A part per billion is similar to $1 in $1 billion. So it's just a quick expression of trying to understand what these concentrations mean and how these concentrations are referenced. Now, in terms of the threat of chemicals, we typically break chemicals into two classes: heavy metals and synthetic organic compounds. Heavy metals tend to not break down in the environment, include things like lead, mercury, arsenic, tin, chromium, zinc, and copper, and their sister compounds. Heavy metals are considered to be extremely toxic. They can be soluble in water and move through groundwater and streams. If absorbed in the body, they interfere with enzyme functioning, and small amounts can cause severe consequences: mental retardation, insanity, and birth defects. An example of this was Minamata disease that occurred in Japan in the 1970s. A chemical company near the village discharged mercury into the river, which then entered into the bay. Mercury bioaccumulated and biomagnified, and basically what happened is cats that were fed fish suffered from acute mercury poisoning and basically were paralyzed and went into comas and died. People in the area started to be concerned, and those that were eating fish also suffered similar symptoms, including mental retardation, insanity, and birth defects, and about 50 people died in this area specifically in relation to this mercury release that had occurred.